Webster, I haven't seen you in so long.
Hi, Miss Words.
What
How
are you doing?
Well, I was just playing with these magnets here and figuring out some interesting stuff about them.
What did you find out?
Well, let me show you. So what I figured out is that if you take one magnet and we place some paper clips on there, they make a chain, but one magnet can only pick up a maximum of 2, and if I try to pick up any more, I can't do it. But if I take 2 magnets and I stick them together, now they look like that. Now,
making it stronger?
Yeah, it seems to make it stronger, so now I can actually chain of 3 paper clips. And I'm not sure what that means, but it feels significant.
Well, I can shed some light on this one a little bit. Yeah, and it's exactly what we've been talking about. We've been talking a lot about attractive forces. If you're talking about the atom, there are things inside the atom that have forces of attraction. Where do you think that might come from?
The forces of attraction. I know opposites attract and like things repel each other.
Right. So what are the things that have opposites inside of an atom?
Okay, we talked about the plum pudding, so there's the positive protons and then there's the negative electrons.
Stop right there.
Okay.
Right? You have 2 charges inside the atom. One's positively charged and the other one's negatively charged.
Okay.
And because they're oppositely charged, they're going to attract each other.
Okay, so opposites attract, so positive protons attract the negative electrons.
Absolutely. And these protons are inside the nucleus, and then the electrons are around the nucleus being attracted to that positiveness.
Okay, so how does this deal with the magnets? What I was figuring out is that if I have one magnet, it can hold 2 paper clips in a chain, and if I have 2 magnets, it can hold 3 paper clips in a chain.
So in other words, the more positive or the more charge you have of the magnet, the stronger the attractive force.
Alright, so basically if this was like 2 protons, they have a stronger hold on the 3 little electrons that are hanging on to it. So this becomes stronger the more protons you add to it.
Exactly. I can show you that with the Bohr model. So let's look back to our Bohr model.
So this looks like what you guys did in class.
Exactly. This is the Bohr models that everyone did in class. And remember what we did? We put the number of protons in the nucleus, and then we designated where the electrons were going in different shells. And if you look at, I'm just going to look at level 2, or energy level 2, going across this way. And if you look at the fact that you have 3 pluses in the nucleus here, and you have 4 pluses in the nucleus next to it, and 5 pluses in the nucleus after that. Well, there's 2 shells here that are holding electrons that are attracted to that +3. And there's only 2 shells that are now attracting a +4, and there are 2 shells of electrons that are attracted to that +5. So as you add positiveness into the nucleus, there's going to be a stronger pull for the electrons into the nucleus.
So if the protons are like magnets, then this one would have 3 magnets, this one would have 4 magnets, and this one would have 5 magnets. And
very good. And what's interesting is that each of these electrons, see these 2 electrons in the first shell, and then this one electron out here, all 3 of these electrons are being pulled with the same amount of force towards that nucleus.
Okay.
It's as if the other electrons didn't even exist. This one electron is being pulled by 3 positives in the nucleus. These 2 electrons each are being pulled with 3 positives from the nucleus.
Okay, so they all have an independent relationship with the proton.
Very good.
Or the nucleus.
With the nucleus. So just imagine that, you guys, that as you add positiveness, you're adding the attractive force for the middle. And each of those electrons, each individually, have their own attractive force for that positiveness inside the nucleus, or the number of protons. Now, another thing that you're going to need to know about is that take a look at the distance that these electrons are from the nucleus.
So these two are really close to the nucleus, but this one's further away from the nucleus.
Let's play around with the magnets again.
Alright, so we have these two magnets here, and I'm noticing that if I bring this closer, it's starting to feel stronger and stronger, and as the distance gets smaller, bam, it pulls together. Now they're really stuck together. They're really, when they're touching.
Now what if you brought two oppositely charged things towards each other? It's like I'm going to push, okay, so there's this force that I want to push it away. And it's definitely, the closer I get, the stronger. If I'm out here, I can't really push it around like with any force. But as I get closer, there's more force, there's a force there that's actually pushing it away. Just like in our magnets, the closer you got to the nucleus, where these two electrons are, the stronger the pull from the nucleus to the electrons. So this electron out here is not being held as strongly with attractive forces as these two in here are. And if you look out here, see this one electron out here?
It's way out.
It's way out, and this one electron is closer, and this one electron is even closer. So this electron here is being held the tightest, while this electron out here is not being held as tightly, or not being attracted as strongly to the nucleus.
Okay, so it sounds like the two things that make it held stronger is if you have more positive charges, that holds it stronger, and the other thing that it makes a difference is how close it is to the nucleus. So if it's farther away, it's held weaker, and if it's closer, it's held stronger.
Absolutely. Very good. You learned a lot today, Mr. Webster.
I sure did.
I hope you guys did too. We'll see you in class.
See you next time.